had to cut open like my palette and like pull it out. He was doing that. He had to put in like so many different shots at once, and I wasn't taking it. He told my mom I was lying about anything.
Okay, I'm going to be writing a lot of things on the board today, definitions and theorems. So it's going to feel a little different, I think, than some of our previous classes. So just heads up. We're going to continue with sequences, and we're going to finish out sequences today, and then we'll start series on Thursday. You have a test a week from Thursday, and that will cover up through, definitely through 8.2. We'll see if we get past 8.2. We're going to, after today, we'll be officially 1 day behind on our schedule. Because sequences always take me 2 days, but I always put them as 1 day on the calendar in the hopes that I'll get through it in 1 day, but it never happens. All right, so limits of a sequence. Or I should say limit of a sequence, not limits. Limit of a sequence. Pardon? We're on sequences. Yep. All right, so given a sequence, this is 8.1 still. All right. Given a sequence, A sub n, and this here is an infinite sequence, all right, so it's a list of numbers. So if someone gives you a sequence, then if the limit as n goes to infinity of your sequence is equal to some number L, then we mean as n gets large, A sub n gets closer to L. So L here is a number. This should look familiar, because when we talked about limits in Calculus 1, it was the same idea. We had different notation though. We use this limit x goes to infinity of f of x equals L. So the main difference is that instead of using the variable x, we're using n, and instead of writing the function f of x, we're using the notation for sequences, which is A sub n. But the idea is the same. As n gets large, our sequence is getting closer and closer to some number. Now, we have some alternative notations for this, right? We can also write this, or we can write A sub n with a little arrow to L. This means the same thing as this. That means what we're saying is as n gets big, as you go further and further out into the list of numbers, it's getting closer and closer to something, all right? So let's look at a couple of very basic examples of limits of sequences. So as an example to start, how about this sequence? 1, 1/2, 1/3, 1/4, ... First of all, what is the definition of this sequence? Can you give me the formula for this sequence? 1 over n, right? 1 over n? Okay, now let's determine what the limit of this sequence is. So we're going to take the limit as n goes to infinity of 1 over n. And now we can kind of go back to what we learned in Cal 1 when we were doing limits. Like, how is this thing behaving? The numerator is just staying fixed, right? And the denominator is headed towards infinity. And anytime you have this situation, a fixed number over a number that gets larger, where does that go? It goes to 0. I mean, you can see it right here, right? 1, 1/2, 1/3, 1/4. These are getting smaller. They're approaching 0. So the answer here is, we could write it this way. 1 over n, arrow 0. Is that pretty straightforward? No magic there? No voodoo craziness here? It behaves the way you think. All right, how about this sequence? 2, 4, 6, 8. So what's the formula for this one? 2n. All right, what's the limit as n goes to infinity of this one? Well, that just goes to infinity, doesn't it? That just goes to infinity. So we would say 2n goes to infinity. You agree? All right. Now some more definitions here. All right. If a sub n converges to L, then, or sorry, if a sub n goes to L, then we say a sub n converges. All right? Now remember, L is a number, right? This right here is a number. I'm even going to stress that a little more. A finite number. So if we actually get a numerical value for what this limit is, then we will say that the sequence converges. Otherwise, we say a sub n diverges. So in the previous two examples, the first one, 1 over n, that converged, right? This example, 2n, diverges. Because it's going to something, but it's not going to a finite number, right? So we would say that this diverges. All right? Now, let's do another one. This one, I'm just going to give you the actual formula right off. I'm not going to list it out. A sub n equals sine n. What do you think? N's going to infinity. What is the sine? What is sine doing? You can almost go back and take a look at the sine curve, right? Like, let's put the sine function in there in red, which is our standard function. That would be f of x equals sine x, right? If we were allowed to plug in any number. Yes? But we're not looking at the function. We're looking at the sequence, and the sequence is only defined for n being equal to 1, then 2, then 3, then 4, right? So we don't get a nice smooth curve. What do we get? Bunch of dots, right? But all those dots have to live on this red curve, don't they? And they're just going to be in different locations. So like you would have to get on your calculator, take sine of 1 and figure out what it is as a decimal. Okay? And it would pop up somewhere. Then you would do like sine of 2, and it would pop up somewhere else. I'm making these up. I don't know if this is where they. Sine of 3 would be, somewhere in the sine of 4, and then sine of 5, sine of 6. You get the idea? And the point is that it's not going to a particular number, is it? As we go out further and further, it's just going to be jumping around, isn't it? All over the place. And so what can we say? It diverges.
Is it going to be like that for all the trig functions?
Well, that would happen for cosine also.
But not for
Tangent would be a little problematic because tangent is periodic and it has a bunch of asymptotes. So like tangent does this, right? Now I would have to draw this in red. and then it does it again, and then does it again, and does it again, right? So if you said, you know, look at this as a sequence, you would have dots, wouldn't you? But they would all live on these tangents. That's obviously not going to any particular value. The issue you might run into, though, well, actually, would you run into it? I don't think you would. And that's, would you ever land on one of the asymptotes? Because then you would be undefined. But all the asymptotes occur at multiples of pi. Pi is an irrational number, and the integers are not irrational, so you would be safe. But that's, no. Okay, yeah. Yeah, it's not happening. Okay, so let's look at another one. A sub n is, how about -1 to the n? What is that doing? It's just going back, -1, 1, -1, 1, -1, 1. So you can, and I would advise you to just write out the first few of these, you know, anytime you can, if it's easy to do. And I think that's obvious that that's not headed to one particular number, right? If we were to graph it, at 1 we're at -1, at 2 we're at 1, and at 3 we're at -1, then 1, then that's what it's doing, right? It's not headed to one place in particular. So this one diverges. So far, okay? All right, what about this? A sub n is n cubed plus 1 over 3n cubed plus 10. Now we're starting to get into something a little more interesting. Any ideas? L'Hopital, good. I was hoping someone would say L'Hopital. Because that's what we would do if this were a function of x, right? If I came in here and I said, hey everyone, what's the limit as x goes to infinity of x cubed plus 1 over 3x cubed plus 10, then you would say, oh, that goes to infinity over infinity, right? So you come in with L'Hopital's rule once. You take the derivative of the top, which is 3x squared, derivative of the bottom, which is 9x squared, and look what happens there. The x squareds cancel, and you just get 1/3. So it converges to 1/3, right? If this were a function of x, can we still use L'Hopital's rule? Doesn't that seem like a natural question? Can we still use L'Hopital's rule? Yes, but we have to be careful. We have to remember L'Hopital's rule requires that we can take a derivative, right? Yes? So go back to Cal 1. The derivative of a function, if I give you a function, the derivative gave you the slope of the tangent line, didn't it? And do y'all remember at all how we actually created that? We start with what we call a base point. We pick another point like this, and we find the slope of the secant line. And then we start moving this point closer to this one. So what happens is I start moving this point along the curve closer and closer, then what happens is you get the 2 points almost on top of each other, and you get the slope of the tangent line when you move them right on top, right? But what you need for this is a nice smooth curve, don't you? So you can drag that point across and bring it closer. We don't have a nice smooth curve, do we? We've got a bunch of dots. So you cannot just straight away say, oh, I'm going to use L'Hopital's rule on that, because you can't take derivatives at points. Does that make sense to you? I'll draw another picture. If I have this sequence of dots, do you see that it makes no sense for me to go to this point right there and ask you what the slope of the tangent line is? Yeah. That makes no sense. Okay? So we can't use the same rule. However, there is a theorem. and we're going to use it. So let me give you the theorem. THM Theorem. If the sequence a sub n can be converted to a function of x such that f is well defined on the interval 1 infinity, then if the limit as x goes to infinity of the function equals L, then so does the limit as n goes to infinity of the sequence. So in other words, that will go to L also. Now I'm kind of giving you like the loose interpretation of the theorem, not the precise one written in the book. But I'm trying to write it in a way that it makes sense to you. So we have to look at a couple of things. We need to see, can we convert that sequence into a function of x? In other words, can we rewrite this as f of x equals n cubed plus 1, did n again, x cubed plus 1 over 3x cubed plus 10. Can I do that in a way that it is well defined on this interval? Now, why am I interested at 1 to infinity? Because my sequence, right? The sequence is going to go from 1 to infinity through the integers, 1, 2, 3, 4, 5. So I really don't care what this function of x is doing anywhere else but here, right? But keep in mind, this includes not only 1, 2, 3, 4, 5, but it also includes like 1.2, 1.5, 1.673, right? All the stuff in between. So if we can define this sequence as a function of x, and it's well defined on this interval, then wherever that goes, our sequence goes. And I think it's pretty obvious because let's say we graph this function, all right? Let's say we graph it. We start at 1 and we were to draw this. Then whatever it does, right, let's say that it goes somewhere, our sequence is on that curve, isn't it? It's a bunch of dots. So it's just some dots on this curve, and so whatever the black function does, the red sequence is going to have to go also to the same place. So it makes sense? And if we can do that, then everything you do to this function, L'Hopital's rule, will give you the same result for up there. All right? So now using that theorem, I'm going to do that problem. So here's how I would do it. Watch the way I write this. All right? So here's the problem, and we're asked to find the limit of this sequence. All right? First thing I'll do, let f of x be equal to x cubed plus 1 over 3x cubed plus 10 for x element of the interval 1 infinity. So I'm just telling you, look, I'm gonna define a function right now, right? Which is basically my sequence with all the n's replaced with x's. This is a well-defined function on that interval. Then the limit as x goes to infinity of this function equals, by L'Hopital's rule, the limit as x goes to infinity of 3x squared over 9x squared, which equals a third. So notice that I'm writing all this down because I need to use the theorem. The theorem requires that I first make like a mental note that I'm switching from a sequence to a function. I do the work on the function, and now from this I will conclude. Therefore, have you all seen this before? 3 dots? That means the word therefore, all right? And we use that in mathematics to mean the word therefore. You'll see me using that a lot. Did I spell that right? It ends with an E. Okay, that's right. Something didn't look right. See, I never write the word therefore. I always write 3 dots. Okay, therefore, all right, therefore, what can we say? A sub n converges to 1/3. What you cannot do, don't do this, or else it'll be counted partially wrong. You cannot write down n cubed plus 1 over 3n cubed plus 10, put a limit as n goes